In our discussions so far, we have talked about the action of a single charged particle, which is given by minus m integral ds and then a minus q into mu dx mu, where this m is the mass of the particle, q is the charge of the particle, mu is the 4 vector field, and dx mu is the coordinate differential defined on the trajectory of that particle. So far we have discussed just a single particle, a relativistic particle of mass m and charge q, and its interaction with a 4 vector field. But what we are going to do today is to discuss how to handle a situation where more than one such particle is involved in the system. That is, we will have the composite system will be like ma, which is the mass of the eighth particle, integral ds, which is for the eighth particle. This is one term which will have a summation over a, where a denotes the indices which tracks the particles number, and then the interaction term will be for eighth particle the charge will be qa, and then integral mu. Mu is a 4 vector field which has got nothing to do with the particle, so it is defined all over space time, so mu will be as it is, but dx mu will again be a coordinate differential defined on the eighth particle's trajectory. So let us write a here also, and we have a summation over q, summation over the eighth a index on this interaction term. Now notice that the first term, which is ma dsa, this doesn't have any field interaction, etc., and so each of these terms will contribute the same thing in the equation of motion, and each of them will lead to the same kind of equation of motion, like du a alpha ds equals whatever. So this part will be same for all the particles for a equal to 1, equal to 2, etc. So this first term is not a big deal, and we know how to handle that. But our main concern here in this lecture will be to deal with the second term, which has the field, the coordinate of the particle, and the charge of the particle, and we will see in this lecture how we can convert this discrete charge particle description to a kind of space-time dependent description. So to do that, let us first note that this qa, let us first draw the trajectory of one such particle. Let us say this one in a space-time diagram like this, where x denotes all three space and this denotes your coordinate time, and this is one, say let us say a equal to 1 is the first particle's trajectory, and it is moving like this, and dxa, by dxa I mean the difference between space-time coordinates x mu plus dx mu and x mu, right? And let us write this a here. So a equal to 1 for this particular case, because a equal to 1 here. So this differential, this is your dxa, right? And mu is defined all over the space time, all over the space time this a is defined, and qa is the charge on top, sitting on top of the particle. This is the situation. If there are more than one such particle, then there will be trajectories like this. Notice that the trajectories will not cross each other, because if they do, then at the crossing point it will mean at the space time event there are two particles at the same point of space at the same time, which is not possible. So trajectories never cross each other. So let us see how we can deal with this kind of a thing. We will see that this can be converted in a way which will suit our purpose. So notice again, qa integral mu dx mu a sum over a. We will write this thing as, instead of qa, which is the charge of eighth particle, we will write rho, which is the function of the space-time coordinates xt, then d3x, that is, it will be a charge density multiplied by a spatial d3x, which is your all space, volume, 3 volume of all space. So rho d3x, charge density multiplied by volume kind of thing in a differential element of space time. So this thing is kind of replacing qa, and there will be of course an integral which will be defined over all space, not time, right? That is, it is defined over all x, y, z coordinates. So this is replacing qa summation, and then your mu is there, which is your regular 4 vector field, and dx mu. and this integral over dx mu is also there, right. Instead of having this integral over dx mu, we will write dx mu dt and then bring in a dt. That is, this dt is, we are basically replacing the integral variable, this thing, from the coordinate differential of the particle's trajectory to the coordinate time. That is, we are bringing in a dt here in the denominator, multiplying by a dt and changing the integration variable. So, if we do that, but to do this and to convince ourselves that this is possible, what we have to do is to define rho xt in such a manner that this term, when this rho d3x integral is done, it produces back the summation over qa kind of thing. And also notice that in this term we have removed this a index is removed. I will explain why we have done that. So, first let us define rho of xt. Rho of xt is defined as qa delta function, the 3-dimensional spatial delta function, x minus x a of t. This is how it is defined, and then of course summation over a. So, what this means? This means, notice that when we are doing a d3x integral over this rho xt, what will happen is d3x integral means this x 3-dimensional x coordinate is being integrated over. So, notice that all the charged particles are moving through the space time. At a given instant of time, all the charged particles are placed somewhere in the space. So, at a given instant of time, if we integrate all over the space coordinate, then only those points where a charged particle qa is present, those points will be picked up by this Dirac delta integral and it will be multiplied by the qa. Therefore, when we do this integral with this kind of a definition of rho a, we will get only those space points which are x equal to x a at time t. Therefore, automatically this integral will automatically ensure that only those x mu's which are x mu a will be surviving. Therefore, this integral will lead us to this thing. So, once we have convinced ourselves that this thing will work, then let us say how to modify this quantity. Notice that there is a d3x over space and dt here, which we can combine to write d4x, which is all space time integral. Then we have rho of xt multiplied by, let us say, dx mu dt. We know that dx mu d tau is your 4 velocity, but here we do not have 4 velocity, we have dx mu dt. This is very important and you should not confuse this with d tau, this is ddt, and we will define this quantity as something called j mu. This thing is defined as j mu. Notice that dx mu is a 4 vector, rho is charge density. So, we do not know whether it is a scalar or not. dt we definitely know is neither a scalar nor a vector, it is a it's one of the components of dx mu, right. So, we will discuss about this, but for the moment let us say we denote this by j mu, and we will have to see whether this j mu acts as a 4 vector or not. Since I am writing it in this form, so you should guess that we will eventually understand that this is actually a 4 vector, but let us just proceed for the moment with this index symbol only, and we are yet to prove that j mu is actually a working 4 vector. Then we are left with mu only, right. Now, notice, so what is this term? This term has now become d4x all space time integral over j mu mu, this thing. Now, let us go back to what we have started with. We started with this kind of an integral where we had q, which is a scalar charge, then mu dx mu was a Lorentz scalar and sum over this. So, basically we were taking one Lorentz scalar action and summing over many such action terms corresponding to many particles. So, it is just sum of it is a sum of several scalar Lorentz scalar quantities. So, the whole thing, this whole interaction term for all the particles summed over is a Lorentz scalar. and then by some such manipulations which we have done here, all these manipulations led us to this form. So, since this form is nothing but a sum of several Lorentz scalars, so this whole thing has to be a Lorentz scalar. Now, d4x we know is a Lorentz scalar integration measure. So, this is an invariant Lorentz scalar thing. Then J mu mu, this index summation also gives us a Lorentz scalar kind of thing. But for this to be a Lorentz scalar, mu we already know is a 4 vector. So, this J mu has to be a proper Lorentz 4 vector. That is, we already know this whole thing is a scalar, we know this is individually a scalar, we know mu is a 4 vector. So, J mu has to be a 4 vector. So, what is the definition of J mu? J mu was defined like rho, which is the charge density, which is a space time dependent quantity, then dx mu, and then denominator was dt. Let us understand this thing properly. Dx mu already behaves as a as a 4 vector. So, this rho and dt individually we know that dt is not a Lorentz scalar. So, therefore, rho also is not a Lorentz scalar, but this rho divided by dt is I mean, when you transform the coordinates from one Lorentz frame to the other Lorentz frame, rho will transform in a strange way, and dt itself will transform in another in a way, and their combination will transform in such a way that their transformation factors will cancel each other. Please understand that we already know how dt transforms, because dt is part of dx mu. So, we know how it transforms. So, correspondingly rho will also transform in a similar manner such that their two transformation factors will cancel each other, and dx mu transforms as a 4 vector. Therefore, this whole thing will transform as a 4 vector. So, without going into the details of how rho transforms and dt transform individually, since we already know this action is a scalar and A is a Lorentz 4 vector, dx mu is d4x is a Lorentz invariant integration measure. So, from this, without going into the details of rho and dt transformation, we can already say J mu will be a 4 vector. So, now you understand that the interaction action for charged particle interacting with a 4 vector field, the interaction action now looks like integral d4x J mu mu. Notice that by doing this trick, what we have achieved is, instead of having an integral over defined only over the trajectory of the particle, we have come to an integral which is defined all over space. This trick is done because this J involves this rho and this rho involves this this Dirac delta function. That is why a discrete trajectory integral is replaced by space time integral. So, this is now our new interaction term. So, the whole system is like several particles are there which are of different rest masses, and these particles are moving in space time along their own trajectories. There are multiple trajectories, and each particle, since they have their individual charges, are interacting with the 4 vector field which has been which is defined all over the space. So, the corresponding interaction term, instead of having a sum of several integrals, we are now having one integral which incorporates all those individual interaction terms. So, so far so good. Now, let us understand, in our last lecture we have discussed that mu, the 4 vector field, can transform in a manner, that is, mu can be transformed to mu prime, which is a new mu, and this new mu is defined as the older mu minus del mu of a scalar factor or scalar function lambda. This we defined in our last class, and we saw that your electromagnetic field, your electromagnetic field tensor is invariant under this thing, and we have discussed how this transformation does not change the action for the particle and does not change the interaction term, etc. Now, in the remainder of this lecture, or maybe in the next piece of lecture, we will discuss why this gauge transformation, when we look at this gauge transformation in combination with this kind of an interaction term, it leads us to the conservation of electrical charge. We will talk about that in the next lecture. Okay, so stay put for the next one.